All right. Well
Awesome.
then. Anyways, since we do have such a short time, I'm sure you guys are onwards to the next workshop that's being held right after this. You are free to PM me at Dacheng.li3 on Discord. You can post any questions, specific ones you have there, or you can post any general questions you have on the communications subsystem channel as well. Additionally, I will have office hours starting every night at about 6 p.m., continuing for as long as I can stay awake. So if you have any questions, please do reach out. I'm happy to speak about this as well as my experiences along this field. Anyways, additionally, if you do have any questions throughout the course of this presentation, feel free to post in the chat or just speak up, and we'll try and get your question answered as soon as possible. So I'm going to start off with amateur radio because that's probably what everyone here is going to be most familiar with. Amateur radio, otherwise known as ham radio, is an American-based, sort of like tier system where they grade how experienced or how much money you're willing to spend on becoming a amateur radio operator. So there are three types of licenses: technician, general, and amateur extra. For all intents and purposes, you don't really need to go above a technician license. However, you are going to general and amateur extra does give you a little bit more flexibility with a lot of other bands and modes. So for example, if you want to prototype something really unique and something a radio system that you built yourself, it's probably worth going to get the amateur extra license, just because you'll probably gain a lot more from studying for those tests, as well as being able to access all those other bands and frequencies. Yeah, basically, just some fun facts about being an amateur radio operator. Don't have to learn Morse code, so it's a lot easier. You can contact people almost anywhere. You can reach out. I'm in LA right now, but I can reach out and radio someone who's in Canada or South America. However, after cell phones and the internet, this isn't really a big deal anymore. But it's worth noting that you are, in case modern civilization does collapse, which does seem a little bit more likely after the events of today, that you might want to consider investing in something like this. So here are some of the U.S. amateur radio bands. Do not worry that you don't have to memorize all of these. And indeed, this isn't entirely accurate. Some bands are more restricted than others, as we'll see in the next picture. This is the frequency allocations for the United States. You don't have to know this. You just have to be able to read it. For example, hey, I'm going to be on the 300 megahertz with my radio, and I need to be able to see, hey, is this band something that we are able to use, and if not, don't try to use that band. Obviously, this should go as a bit of a theme in today's presentation, but a lot of radio licensing and design is heavily centered around the various regulations from the ITU, the FCC, as well as a few others. So it is worth noting that you can't just sketch out an entire radio system and expect it to be approved automatically. You have to go about it meticulously, and it is probably worth the investment, especially if your team isn't that heavily radio focused, to just buying components off the shelf and the like. All right, here are some important terms that you guys should become more familiar with. Frequency, bandwidth. I won't read all of these, but in order to design a proper radio system, you will know more or less all of these terms. Don't worry, there's more. you don't have to necessarily have all of these memorized, nor do you have to have all of them listed out and planned for throughout the course of this hackathon. However, if you are trying to get a CubeSat to fly, you do have to know all this stuff. Anyways, so we're going to start from the basics. What is a radio? I often ask myself that question. So if you're at all curious to my level of competency, that should tell you a lot. But in any case, a radio is basically something that you can send electricity. Like this diagram basically tells you a lot, right? So you have a power supply and oscillator. That oscillator is the actual devices generating your radio waves. And then afterwards, your signal goes through a modulator in which you're actually able to fuse your signal data with your actual carrier wave. And then it's broadcast sometimes through an amplifier, sometimes not, through an antenna. And if you check my Discord little like snippet, you'll see that I have this antennas are spicy metal. That's basically the case. You can build an antenna out of just about anything. Some antennas you'll be able to find out there that are like thousands and thousands of dollars, or you can go out and grab like a $2 roll, $2 tape measure from like Home Depot or something, and try and build an antenna out of that. Won't work as well, but it will still be able to transmit and receive carrier waves. And at the end of the day, for a competition that centers around building the minimum viable CubeSat, that may be an option that you want to consider. The system basically works just as well in reverse. You have your antenna to receive carrier waves, at which point it's turned through a tuner, a detector, and an amplifier, or a signal modulator, so that you could read it into your computer or something. It is worth noting that you don't have to know the exact internals of how of your radio. You just have to get it to broadcast from point A to point B, and that's good enough, right? So modulation. Modulation is a little bit more technical of a subject, and I won't get into it as heavily, but you can think of it as the beat that if you're someone that listens to a lot of music, it's the beat and the tempo that your carrier wave is actually dancing to. So there's tons and tons, and we can spend an entire presentation going through all the benefits and downsides of these various modulations, and basically figure out exactly which way is best for your carrier wave to send data. However, it's essentially worth noting that there's a lot of very common ones that are used in CubeSats: GMSK, GFSK, LoRa. Sometimes you see a little bit of SSB. These modulations all have their benefits inside and downsides. And if you want to know like a little bit more about the nitty gritty of it, we can probably talk about that a little bit more. But in essence, your modulation will have a heavy effect on how much data you can transmit. So for example, for an FM carrier wave, which is something you'll be able to see here, FM basically means frequency modulated. So your frequency will change, a little bit to denote different data. And obviously, this is you can see it down here. This sort of carrier wave is good for something like if you're transmitting binary code from point A to point B. However, because you are only transmitting signals like this, you don't have that much data to work with. On the other hand, if you have a modulation like this, which is GFSK, you have now four you have four places where you'll be able to send data. I'm not really going to get into more of how modulation works. Not in not when I only have 40 more minutes left and like 20 slides to get through. But it is something that for you to design a good radio system that you'll have to be aware of. Now, on to the meat of what we're going to be covering today. So, link budgeting is probably what your comm system is going to be very heavily oriented around. So, a link budget basically simplifies to, do I have enough signal strength to send my data from point A to point B? And as with any other budget of any sort, you have to account for all of your inputs and outputs. So like, if I'm budgeting for my monthly expenditures, I have to, be aware of, hey, how much am I spending on gas? How much am I spending on my utilities? And as well as all the miscellaneous stuff that I happen to buy. If I always see something nice on Amazon, do I want to buy it? Do I not? Your link budget will work in much the same way. So at the moment of transmission, your signal strength is like maxed out, right? You can't really see my arm because of my virtual background, but trust me, like it's like up here somewhere. There we go. And then as your signal moves through each element of your system, it'll gradually lose more and more signal strength. So one of the main losses that you'll be expect to see, especially with CubeSat design, is path loss. Space and your CubeSat is generally really far away from your ground station. And as such, your signal will have to travel a long way and it'll lose a lot of energy, just trying to get down to Earth. Another really big loss area that you should work around is your pointing. Basically, CubeSats, at least some of them, usually operate directional antennas. And we'll get into what that means in a little bit. But basically, with directional antennas, the direction that in which it's pointing matters a lot. So, for example, if we have two directional antennas looking at each other, and pretend that like this fist over here is the ground, it is your ground station. If my directional antenna really only works this way, and my CubeSat does something funky and it's pointed like this now, it's not going to be able to send that signal, a really good signal anyways, down to your ground station. Is there any confusion on what I've described so far? No? Great.
No.
Okay. Anyways, there's a lot of loss areas for you to consider. Essentially, you should be, in an ideal system, you should be considering every single element of that you can lose. So like like your cable loss, that is something that you should definitely consider. Foliage loss if your ground station's set up in a forest somewhere or something. If your ground station set up maybe like in an area that's really dry or really wet, like if any of you are unlucky enough to be stuck in Florida right now, you should be considering any loss that you may experience from like rain, as well as general humidity. Anyways, consider everything. If you're not able to consider everything, consider as much of it as you can. Anyways, on to more hardware directed stuff. We're making good time. All right, so there's two main types of antennas, your directional antennas and your omnidirectional antennas. Unfortunately, because reality kind of sucks, there's no true omnidirectional antenna. There will always be some areas where you have a good amount of loss. And like if you're interested in creating like a spherical a radiator, first of all, why would you? Second of all, no, like know that you won't be able to get good coverage everywhere, which is why a lot of CubeSats choose to go with directional antennas. So pictured up here is what's known as a patch antenna. A patch antenna is something that, well, it's a patch. It goes on one side of your CubeSat, and it basically, the way you orient it is you just have to orient the entire damn CubeSat. And when it's pointed down to Earth, you're able to get a good link, but you're able to get a good link from your CubeSat in space all the way down to your ground station on the ground. Now, I suspect that that your choice in antennas is largely going to be dependent on other factors, including exactly what frequency you're working at, as well as like exactly which orbit you choose. However, just note that patch antennas are a very good way, albeit a very expensive way, for you to transmit data to the ground, simply because they're almost perfectly designed, I feel, for the CubeSat form factor. They're very small. Like you are limited in the fact that you have to establish a good pointing vector. So heavily focus on your ADAC system if possible. But know that patch antennas are a very good, reliable way to transmit signals. The other option, of course, is omnidirectional. Omnidirectionals are, like they spread. They're not very focused in how they spread your signal. So you can think of it as when you're watering the lawn. Your directional antenna is like that one setting on those little like nozzle guns that jets all of your water at one spot. It's a very focused beam. On the other hand, your omnidirectional antenna is more like your sprinkler. It'll spread water everywhere, but you can be pretty sure that you'll at least get it like some of the way, right? And in this picture we have pictured someone has used or like cut up some poor tape measure and is using the guts of this tape measure for their antenna. These antennas can be seen in real life as well. Like if any of you guys know Project Elfin, which is another UCLA development, they are actually using one of these type of antennas, and they have very good results in broadcasting their data to the ground. Unfortunately, with Elfin, Elfin actually spins due to the nature of its scientific instrument, and that sometimes causes trouble with connections. Again, not all the time, and like a system like this would function perfectly well, even if it isn't directly pointed to the ground, or like even if it isn't terribly well oriented. It's just going to take a little bit more transmit power for you to do so. All right, choice of radios. Two main radios. I'm going to also try and cover frequency selection in this. Basically, you have two main choices. Well, three if we're honest. A transceiver, which is a combination of a transmitter and a receiver, because radio scientists are terrible at naming things. These guys are usually pretty expensive. And usually if one part of your system goes, the entire comm system is going to fail anyways. But this choice is usually very good for the CubeSat form factor, because now you only have one major component outside of your antenna that you have to have internal to your spacecraft. Some versions allow you to like mix and match some frequencies, but that usually isn't terribly common, and you'll probably have to like pay a little bit extra to get it. And these units are often very limited in the way that they can transmit. So often with transceivers, you'll run into problems with like both transmitting and receiving data at the same time, because since they're both on the system, one signal is going to have to like wait before it's able to be transmitted. On the other hand, if you have a separate transceiver and a transmitter or receiver, you run into like problems of cost. And you'll note that I have a cost as a con for both of these. That's because I'm a project manager, and communications gear is expensive, especially if you buy it off the shelf. But anyways, uh, you know, these are much more flexible because you can choose two different frequency bands. So if you want your uplink, your ground to space to be in one frequency, but you want to transmit your data down in another frequency and have the two operating in parallel, you can definitely do that with this sort of system, and that's much easier to accomplish than if you were relying on a transceiver. Now, you might be asking, why would I want to do this? The reason for that is if you have something that just eats up lots and lots of data that you have to get to the ground, but if you're only sending simple commands up your satellite, it can be really difficult to say, hey, do we want to over-engineer the uplink and sort of neglect the downlink, or do we want to do that vice versa? Well, a separate transmitter and a receiver function will work around that kink, because now you have two different frequencies. I can have VHF, UHF for my uplink, something that doesn't do terribly well with high data rates, and like X or like Ku-band for my downlink, something that will handle very well with large packets of data. Anyways, the third option that you can have is just buying like a transmitter. This is what's traditionally known as a CubeSat. So-called because the only thing it's good for is beeping in space, and like that'll fit the definition of a minimum viable CubeSat. Not terribly creative, but if you're really stuck on not having a good communications team or what have you, or if you just don't want to mess with like having like sophisticated ground to like space or something, that'll work perfectly well as well. Now, will it win the competition? That's your choice. And I guess I'll spend a few minutes touching on frequency choice in this page. So as CubeSat designers, you will no doubt know that you have a lot of choices. So if we go back a few slides to this frequency allocations diagram, the radio spectrum is hilariously wide. So you have choices available anywhere from high frequency, very high frequency, ultra high frequency, extra high frequency, and I think one more. But you should always decide, hey, how much data am I do I need to transmit? So for example, SpaceX and Starlink, they rely almost entirely on Ku-band, because which is a very high frequency sort of system, and they have that's because they have tons of data that they need to transmit. I mean, think about like streaming your average like YouTube video, right? Like there is tons of data just in like a short like 30-second video that will need to be transmitted, for you to watch smoothly. Now, on the other hand, Ku-band is not terribly great for maintaining signal coherence through long distances. So you either have to have a really powerful radio, or you would want to lower your frequency limit. And obviously, Ku-band is terribly expensive, and really only good for like telecommunication communication stuff. Anyways, is there any questions up to here? Great. Okay, so we're going to do a case study of a hypothetical ground station. And if you guys like, I'm going to copy and paste this spreadsheet into the Google Drive. It is in the Zoom chat. So this is an example of a link budget. Now, this is very, very, very powerful in planning out your radio system, right? So can everyone see my screen, by the way? Right. Tough crowd. So this is one that I've been working around for quite some time, and it's extremely powerful. It accounts for spacecraft and what you need to transmit, your path loss, and its effects at your ground station, as well as the data rate that you need. So I'm not going to go terribly deep into this. A lot of the stuff is pulled from various sites, but like you are more than welcome to use this document as a template in planning your radio system. But just note that you might not have all of the values, and that's okay. No one's expecting you to simulate, like if you have 2 amps or amplifiers, no one is expecting you to have everything planned out here. Sometimes if you don't know the effective noise temperature, no one's gonna care. Just copy some values from somewhere, because at the end of the day, you and your teams will be planning and designing a very I don't want to say shoddy, but a very low budget satellite. And these things, if it ever goes to design, will be something that you guys can work around, right? So we'll get started, and I'll show you how this diagram works essentially. So carrier frequency is the frequency that you're transmitting. So say if I want to transmit at 915 megahertz, which is LoRa, I'll put 915 here, and it's got a provided symbol. A lot of these formulas are pulled from the NewsMad. By the way, if you guys want to read the NewsMad, great book. Probably not like like good light reading, but it'll teach you everything you need to know to build a satellite. For your transmit power output, a lot of transmitters will be 1-watt transmitters. But like again, like this is here, it'll you should prior to building your satellite, always plan it out first. So I'll put 1-watt because that's what a lot of data sheets will say. But yeah. All right, your peak antenna gain. Obviously, this is something that you're also going to have to plan out through your research and data sheets. But for sake of discussion, we'll say like this is we're working with a 4 decibel antenna, and there we go. That's what we're working with right out of our spacecraft. Now, we don't have a path. We're gonna just say that it's like 2,000 kilometers. Sorry, 2,000 kilometers, and that's how much signal strength we're losing from just being so far away from the Earth. And obviously polarization loss, you don't want to have much, if any, polarization loss. So going back to our antennas, I lied. There's a lot more that goes into designing an antenna and planning for an antenna than just, hey, are we doing directional or omnidirectional? So antennas often have what's called a polarization. So you either have your signal that's being left-hand polarized, left hand, or right-hand polarized. You don't need to know exactly what that means. You just need to know that you need to match right with right or left with left. Otherwise, you're going to lose a tremendous amount of signal. So if you're planning to use certain antennas, please check that it is either your system is not like right left right, because like there is no way that will ever transmit a reliable signal to the ground. So we'll say 1 decibel loss for this. Now, onward to the ground station, right? So this is the receiving antenna pointing loss. Obviously, you want your antenna to be pointed as well as possible to your ground station antenna. And that is something that you'll have to probably simulate, either simulate or just try and design around. I mean, this is what I was mentioning previously when I was saying that, hey, you should definitely try and work out a lot of kinks with your ADAC system, if at all possible, because your ADAC system is what's responsible for your pointing. And if you can't maintain a good, like if your system, if your spacecraft's like spinning like end over end, you're never going to get a good, signal on the ground, no matter how powerful or how much money you throw at your comm system. So, if you learn anything from participating in this hackathon, know that spacecraft design is a holistic process, and that you have to combine elements from a lot of different systems in order to design a good overall spacecraft. But in this example, we'll say that we're at a decibel loss. Don't worry about it. Antenna gain, obviously something you'll have to research. We'll say like we're working with a 20 decibel antenna. And obviously, this ground station has 2 amplifiers. So we'll leave those there if your
is the antenna gain in dBi?
Sorry?
I'm sorry. Is the antenna gain in dBi or dB?
So,
like compared to an isotropic antenna, or just is that actual power gain?
You should always try and compare your antennas to an isotropic, because like that's the best result you're ever going to get, right?
Okay, so it's dBi then.
Yeah.
Okay. Thanks.
But radios is a little bit black magic at times, even for me. You should know that you're like a lot of there are like tons and tons of there's DBIC here, there's DBI, there's DBW. There are some things that you can just quietly smooth over, and I'm not saying that I encourage that, but if you miss a unit here and there because you're rushed and trying to get a comm system designed in 48 hours, no one's going to like chalk and say like, hey, like the system's worthless, right? All that requires is that you convert your values from one to another. Anyways, moving on. Effective system noise temperature. Hey, how hot is your system? Your reference temperature. This is pulling from this MAD book, as well as like your receiver noise. No one saw anything. So obviously, like you're not going to have a lot of these values because you don't have the hardware to measure any of these. But just rely on what data sheets you have and try and calculate what you can't. And at the end of the day, if you can supply an educated guess, that's better than just leaving something blank, right? Anyways, some other components, not terribly important for the context of this presentation. If you would like, we can walk through some of the finer points of in the system, like ground system design and stuff. I have looked into this heavily. Anyways, onwards to your data rate. Like obviously, you're going to have to choose how choose your data rate. But for context of this, we'll say like 2,000 bytes per second. Bandwidth, also something you can definitely tune. For 915 megahertz, that's usually around, I think it's around 1 or 2 megahertz of bandwidth. We'll say like 50,000 for right now. And there we go. Your bit error rate is going to be heavily dependent on what modulation you use, but know that this is something that you can look up and will be referenced to you. I don't remember what the this modulation was using, but I think I can assume. I think I can assume 2 dBs required and 10 for this. No, sorry, this is the opposite way. 1 to the negative fifth. Again, I just approximated those values from what I remembered, but you should be researching this stuff, right? Anyways. So at the end of it, you get what's called a link margin. So what that means is, hey, I have 7.5 decibels of signal power, right? No, that's being received, at my ground station. Your goal should be then to compare it to your noise floor and say, hey, am I ever going to be able to hear my signal? After all said and done. And you should always aim to have a higher link margin if at all possible. Because think about it like your your usual budget, right? At the end of the day, you don't want to be like you don't want to have paid off your rent and your utilities and whatnot and left with $30. You want to plan and budget your account enough so that you're not below the poverty line essentially. Anyways, we've got about 15 minutes left. I want to save 5 minutes at the end for Q&A. So let's push forward with the last of this stuff. There is also a uplink budget that has been provided for you. Again, some values are just ripped off of the previous one. But do your due diligence, research all these values, and just if you can't source it from a data sheet or simulate it through something like FreeFlyer or SDK or whatever your orbital simulation link budget estimation system will be, an estimated guess doesn't hurt, especially at in the early stage of design, right? All right, back at it. Yeah. All right. Is there any questions up to here? I know I just covered a lot. No. Okay, great. Moving on. Packets and error correction. So it is a basic given that you will not receive 100% of the signals that you send, no matter how good your link margin is, right? somewhere along the way, your signal is going to get distorted. It's going to lose coherency, and you're not going to be able to receive the entire packet of information that you've sent out. So, however, you can do this thing called error correction. So, like you can put in parity bits in your transmission. You can some people also choose to just send their message twice because they're weird. There's tons and tons of checksums that you can use. You should probably read into a little bit of Reed Solomon, Reed Miller for a little bit more detailed stuff. But you will. It's not probably something that you'll get to over the course of your design because error correction is one of the more complex things that you do. And for me, at least, I'd rather see an entire system designed out than exactly how I'm going to account for every last bit of data that I send, right? And it's worth sometimes noting that this can be handled by the CDNH team. It's also sometimes handled by a transmitter. You just have to try and shift this around so that it's not it's not like a game breaker, but it's not also something that is going to hold you up essentially. So onwards to software-defined radios. What is a software-defined radio? How can I use one? I'm sure you've seen one just laying around. I've got two here. I can't find them. But anyways, I've got two B100 minis from UTSC, I think, and they're a very reliable piece of kit, but they're also like $800. So anyways, software-defined radios is exactly what it says on the tin, right? Like it's your radio, but its function is decided by software. So this is a very powerful development, especially for ground stations as well as CubeSats, because it allows you with an adequate antenna setup to basically control exactly what frequencies and modulations that you use, and all you have to do is code it in. This stands in contrast to traditional transmitters, in which this is all decided by the hardware that you put in. Now, this is a very complex bit. I don't expect anyone to pursue a solution that revolves around software-defined radios, but it is worth mentioning because your transmitter will essentially you'll basically double or triple your effective functionality of your system, simply because now you have access to a whole range of frequencies and a whole range of modulations that for some reason that your system doesn't work, and when it's in orbit or something, you can implement a software patch and shift your frequency band tremendously. And I don't have to say how powerful this can become if it's used properly. If it's not used properly, then you have someone messing around with Linux and GNU Radio for a month, 2 months, and you don't get anything done. Anyways, the last bit I want to cover is how to support radio systems. And you'll see that I have outlined that communication systems are very, very expensive. Sometimes if you buy components off the shelf, your system can cost about half of what your total system allocation can become. However, it's also tremendously important. There's no reason to have a sophisticated science instrument up in space if you can't beam that data back onto the ground. So to support radio systems, you should have a reliable power system, EPS. You should have a reliable ADAC system so that you don't lose a lot of your link over to pointing loss. And obviously, you're going to want to have a reliable connection with your flight computer. There's nothing more frustrating to designing a system if parts of it just fail completely and you're left with a brick that's floating in low Earth orbit. Now, obviously, or maybe somewhat not obviously, your satellite is going to want to target and send data to the ground, which means like as with all radio networks, you need two components at heart: one on the ground, which you can't see because my fist is in my virtual background, and one in space. And they need to be, and if you don't have plans to, if you don't have like one or the other, it can be exceedingly difficult to design a system that will support both, right? Anyways, moving on. Last part we're going to cover is licensing, and we have about 1 more minute, so I want to just breeze through this. There's tons and tons of licensing, licensing like bureaus and agencies to watch out for, and they'll probably just look over your spacecraft and like all of its, especially your link margin, which means like you'll have to like always have that defined as best as possible. And this isn't necessarily something that you'll have to consider for this spacecraft, for this competition, but I just thought it'd be a nice thing to note in there. Just something to definitely emphasize how complex these systems can become, and as a little precautionary measure to not design anything that can't go through regulations, right? Anyways, it is now 5:55. My throat is sore. Does anyone have any questions before I close out this presentation? Are there packages online for doing some of the error correction algs? What do you mean packages online? Are you talking about like software? Like how would you go about building a pipeline for your data? Okay. So let's assume that I already have a working functional ground station. Because honestly, like that's not a terrible assessment. If you can't build one right now, you can probably rent one out. AWS has a fairly reliable service they provide. And there are a lot of open source options out there that you can attempt to use. So like I'm building a spacecraft. I've got my flight computer. I've got my like black box sensor of a sort that's generating data, and that's feeding directly to my to my flight computer. My flight computer does whatever it is, and it sends that packet of information to my transceiver. There are some transceivers, especially if you buy one of the more expensive off-the-shelf components, that will essentially handle your error correction for you. And that's not to say that like you should be entirely reliant on that, but it is something that you can use. It'll just drive up your budget a little bit. But once once that transmitter gets that data and it sends back to the ground, you have to have your ground station configured in such a way that it'll pull the good data, the gold, right, from the mud, which is the rest of your your parity bits, your duplicated transmit data, and whatnot. And especially if you're using like a service like AWS Ground Station, a lot of that stuff can be really automated for you. Sorry, my voice is like kind of sore. I'm terribly sorry. Yeah, AX25, Reed Solomon is also a good one. But at the end of the day, if you don't want to mess with any of that, like having a simple checksum, like, hey, this is how long my message is supposed to be, and then like packaging that into your like your message, and then once the signal is on the ground, and say, hey, my message was supposed to be 8 lines long, but we only got 5, so we're missing part of the data, and let's maybe looking at this data, hey, well, these are the sections of data we're missing. On the next pass, let's get those transmitted, if at all possible. So like, don't overcomplicate it, but also don't try and, but like, don't also don't neglect it, right? Sorry if that wasn't terribly clear. All right, any other questions?
All right. Well, we're right up against the time slot, so
yeah, no,
yeah.
I rushed through that like we are going today, boy.
If anyone has additional questions for Dacheng, he is of course available on the Discord. Are you gonna be available throughout the weekend?
If I'm not, feel free to drop any messages you have over to the Discord channel, and I will attempt to get to it when I get a chance. Yeah, experienced comm people are relatively rare, so I do encourage all of you guys to help each other whenever possible. One of the things that I have noticed from my time as a radio engineer is that radio personnel are in short supply everywhere, and if you got, we should be helping each other as much as possible, right?
All right.
Dire Wolf is pretty reliable, yeah.
Thank you, Dacheng. I'm gonna bounce over to start up the next workshop, but yeah, we'll see everyone throughout the course of the week and the weekend, and looking forward to seeing what you guys are able to put together.
Yeah. All right. How do I do, everyone? Cheers. Cheers, Michael.